So let me remind you where we were. So we've been talking about this geometric representation. And so what we do is we start with a Coxeter system like this. Given that, we talked about how we could make a geometric realization that I should come over here. So we talked about how we could really, so this was the example of the symmetric group S3, and we talked about how we could really think of the group operations as geometric operations on a vector space. So, each one of them is an invertible linear transformation, and so in this case, the generators S1 and S2 act as reflection across this line and this line. And in general, we saw that these generators act as something that is kind of like reflections, not always exactly a reflection, but kind of like a reflection. Okay. Then we talked about defining the root system, and the way we would define it is that we, in this construction, we started by starting with a basis, which in this case is alpha 1 and alpha 2 for our vector space that we're playing with. And we talked about how the root system is just obtained by applying these geometric operations to alpha 1 and alpha 2 in every possible way. And so the root system that we got in this case was given by alpha 1, alpha 2, and then these other 4 roots. So it's these 6 black vectors. So that's the root system. And we called it root system capital pi. Okay. And we talked about how, now there's a usual piece of notation that I haven't told you, which is that we usually call delta the simple roots, in that case alpha 1 and alpha 2. Okay? So simple roots. So these are just, for each one of the generators in S, we have a root which we call the simple root. So if S is S1 up to Sk, then the simple roots are just alpha 1 up to alpha k. Okay. Okay. So what else? We talked about how each one of the roots in the root system corresponded to a reflection that was a reflection in the group. So this is what we talked about last time, where the geometric reflection by W alpha I. So what does this mean? Well, alpha I is one of these simple roots, and W is some group element that acts on it. And so this is just some root. And we talked about how this corresponded to the action of the reflection given by W S W inverse. Okay. And so then we talked about how there was basically this correspondence between roots that look like this and reflections that look like this. So it's a one-to-one correspondence between this geometric set of roots and this algebraic set of the reflections in the Coxeter group. So this is what we proved last time. Okay. Now, let me remind you of something that we proved last time, or I guess 2 classes ago, which was the following. We proved, now, I don't know if you're taking notes, I'm going to tell you that I'm going to write something here, which was our old result, and then I'm going to erase it and write our new result that looks very similar. Okay? So our old result said that if you had a generator, and then this means that we have a simple root, then we talked about how we could characterize the property of the length function. So this property that if you multiply by generator Si, you get a bigger element. We could characterize this geometrically, by saying that if we make that group element act on the corresponding root, then we get a positive root. And the length of WSI is less than the length of W if and only if W takes alpha I to a negative root. Okay. So we saw that basically the length function in some sense characterizes when group elements take positive roots to positive or to negative roots. Now, what I want to do now is basically prove the exact same proposition, but now not just by multiplying by a simple root, but by multiplying by an arbitrary, not by multiplying by a generator, but multiplying by an arbitrary reflection. And if you remember, this is kind of the difference between the weak order and the Brewer order. So the weak order is defined by basically you go from W to WSI if this is bigger than this. I guess this would be the right weak order. And in the Brewer order, we allowed to go from W to W times T, where this was an arbitrary reflection. And so we want to understand when that is true geometrically. So then what I want to do is just replace this by some arbitrary reflection. And now we know that reflections correspond to roots. So instead of having a simple root, I'm going to have just an arbitrary root. So alpha is the corresponding root. Okay. And then it's as easy as you could imagine. The same exact result is true. Okay. So let's prove this. So the way I'm going to prove this is, let me first remind you that when we prove this for the other version, for simple roots and for generators, the first thing that I did is that I showed to you that these two statements were basically equivalent to each other, and that if I proved one of them, then I got the other one for free. And so here it's exactly the same. So it's easy to see that they're equivalent. And so, for example, 2 implies 1. If I call this 2 and this 1. Okay. And so let me just prove 2. Okay. So let's prove 2 by saying we suppose that the length of WT is less than the length of W. Okay. Now, the thing about this is that we understand when this happens, right? Because this is exactly the setup of the exchange property. The exchange property tells us exactly when you multiply by a reflection and you become shorter. So the way that this goes is that if we take some reduced word for W, then we know exactly what T has to be. T has to be a reflection obtained by starting from SK, going down, and then back up. So let's say that it's SK down to SI plus 1 to SI. then up to Si plus 1, up to Sk. We know by the exchange lemma that the exchange property, that W and T must be of this form. Okay. Now, why is this a reflection? Well, we talked about this many times, but let me reiterate it. That the reason is, first of all, because it's palindromic, and so that's one characterization we have. But we want to realize it explicitly as a conjugate of a generator, and the way we do that is by calling this thing U, and this thing is U inverse, right? And then T is the conjugate of Si by U. Okay. Now, the reason that I want to do that explicitly is that I want to use this dictionary that tells me how to go from a reflection to a root. Okay? So if I want to know, I mean, I said T was a reflection and alpha was the corresponding root, but I want to get a handle on exactly what alpha is, and I know that now, because if a reflection is of this form, then I know that alpha is of this form. Okay? So I've written my reflection in the form U Si U inverse, and that allows me to write my root as U times alpha I. So alpha is U alpha I. Okay. So, and now that I have a formula for alpha, I can actually try to plug into here and hope that I can prove that W times alpha is negative. Okay. So what's W times alpha? Well, alpha is U times alpha I, so this is W U alpha I. Okay. And now I want to know whether this is positive or negative. Now you see that actually a question like this is exactly answered by the previous version of this proposition. Yeah? Because what I'm asking is, I take a group element and I multiply it by a simple root, and I'm asking whether that's positive or negative. Yeah? So this I will be able to answer by the previous version of this proposition. Now, what is W times U? Well, let's just plug in, because we know what they are. W is S1 up to Sk, and U is Sk down to Si plus 1. Right. And then we know that there's going to be a lot of canceling going on here. These guys are all going to cancel everything up to Si plus 1. And so what I'm going to get is S1 up to Si, and then alpha I. Okay? And so what I'm asking is just, is this group element acting on alpha I going to send it to a positive root or to a negative root? And we know that this is bigger than 0 if and only if, or rather, I want to show that it's less than 0. So if I wanted to prove that this is less than 0, then this is a geometric statement that has an algebraic counterpart by the previous version of this proposition. It tells me that if I want to check this, then what I need to check is whether the length of S1 up to Si increases or decreases when I multiply by this generator corresponding to alpha I. If I want less than here, I should have less than here. And so this is what I'm left with checking. And then you see this is absolutely clear because these guys cancel each other. And so this guy has length I minus 1. This guy has length I. Okay. So this is true, and that means that this is true. End of proof. Okay. Any questions about this proof? I should realize that we're getting a little better at mixing the algebra and the geometry here, because in this proof, we ended up using this geometry algebra dictionary, and we kind of didn't translate it freely. Here, we used our old combinatorial lemma on the exchange property. Then we translated it into geometry, and then we translated it back to algebra. So we're getting better at this. Okay. But so that allows me to characterize, for example, the Brewer order geometrically. So if I want to know if W is less than or bigger than W times T in the Brewer order, then I can just do the geometric operation of letting the geometric operator for W act on the root alpha and see whether it becomes positive or negative. Okay. So I'm going to switch topics a little bit. So are there any questions about this before I switch? Look all right. So I want to refine the geometry a little bit more. I want to understand this picture that we keep talking about. I want to understand it even better. Okay. We understand some things about it. For example, that roots correspond to reflections. There's several things that we understand. But now I want to do even more. So let me show you exactly what I want to do. And so I want to talk about something called the fundamental domain. Now, let me just tell you the general story of what I want to tell you about. Basically, whenever I've drawn this picture, and I drew this picture in the very first day of class, I talked about reflecting hyperplanes and things like this. I talked about mirrors, but I haven't actually made that concrete for you. So far, what is concrete in this picture, and we have proved, is roots and how the group acts on the roots. Okay? So we do know that we have a root system, and it looks like this. And then we know that we have some operations that act on the root system. But now I want to actually understand this idea of a mirror system and how precise I can make that. So how do I make this picture precise? Well, let me first make a disclaimer here about what I'm going to say, which is the following. For today's class, I'm going to assume that my picture is Euclidean. Okay? So today, we're going to assume that my picture is Euclidean, meaning that V is Euclidean space, and my linear form is exactly the inner product in Euclidean space, okay? Dot product. Now, I haven't told you exactly when you can do this. I told you that for some Coxeter groups, you can draw the picture in a Euclidean way, like we did for S3. And I told you that for some Coxeter groups, it's just impossible. Okay? And so necessarily what that means, if I'm assuming that I'm Euclidean here, basically I'm not doing this for every Coxeter group. Now, let me tell you the fact, which is that if your Coxeter group is finite, then you can always realize it in a Euclidean space. And that's actually an if and only if. So this is a very nice theorem that says actually if you're finite, then you can live in Euclidean space, and if you're infinite, then you can't. Okay? And so basically this is equivalent to saying that my group is finite. Okay? And I'll just tell you that what I'm doing today, you can do for infinite groups. It's a little bit more complicated, but I want to just do it in this case, which is the most important one for us. So this also works for W infinite with some extra work. Okay. But so you see, what I have then is basically that I have these simple roots alpha 1 up to alpha k, which are a basis of a Euclidean space. So now I can think that V is just R to the k. And this is a basis, and my inner product is Euclidean. And so what I want to do is the following. For each root, I mean, I want to make that picture precise. And so for each root, I'm going to define the hyperplane. Okay. So what is the hyperplane? Well, basically, it's consisting of the things that are orthogonal to my root. Okay. So this consists of the lambdas in V such that they are orthogonal with alpha. And I should tell you that because I'm allowing myself to be Euclidean, and because I'm allowing this to really be the dot product, then today I'm going to just write it like this. So dot product, and that way you'll remember that this is just the dot product that you're used to. Okay? So if I have some vector alpha, then this defines to me a hyperplane that is just the things that are perpendicular to this. Okay? Now, basically, this hyperplane and any hyperplane in a real space cuts up my space into two pieces, right? I mean, this hyperplane is given by a linear equation. A times x plus b times y plus c times z equals 0. And then you have the side where that equation is bigger than 0 and when it's less than 0. And so I'm going to call A sub alpha the positive side of the hyperplane. Okay. The things that have positive dot product with alpha. Okay. So let's go to this picture over here. And you see that, for example, for alpha 1, I mean, this is really R2 with the usual Euclidean geometry. So the hyperplane perpendicular to alpha 1 is just this one right here. Okay? And so really, this is what I'm calling H1. Okay? The things that are perpendicular to alpha 1. And the half space is basically the things that have positive dot product with alpha 1. And so they are the things that live over here. So this is A1. Okay? And in the same way, alpha 2, the things that are perpendicular to it are this hyperplane. Okay, H2. Make this a little bigger so it shows. And then the things that have positive dot product are the ones that are on this side of the hyperplane. This whole half space. Okay. But I'm not just doing this for the simple roots, I'm doing it for all the positive roots. Okay. And I have a third positive root here, which is alpha. Okay. And so that has a hyperplane perpendicular to it. Let's call it, I don't know, H in this case. And a positive side, which is this side. The things that have an acute angle with alpha. Okay. So then the next thing I want to do is define C to be basically the set of points there that are on the positive side of every hyperplane. Okay? So one way of writing this is that you intersect for each positive root the positive half space. Okay? So, and then I'm going to define D to be the closure of C. Okay, so let's see what this means in this picture. So what's C? Well, C is the set of points that is on the positive side of each one of the hyperplanes. Okay, so I have to be on this side of this hyperplane, I have to be on this side of this hyperplane, and I have to be on this side of this hyperplane, and I have to step back to see what it is. So that's this little wedge right here. Right? So this is what I'm calling C. Now, does C contain these rays? Well, it doesn't, because the inequalities that I use to define C are strict inequalities. Okay, and sometimes I want to talk about the open cone that doesn't contain the rays, and sometimes I just want to close it because it'll be more useful. Okay, and so D is going to be this open cone together with all of its faces. And so if I include this part right here and this part right here, then this becomes D. Okay. And so that's what I'm defining. So this is the set of things that have non-negative dot product for all alpha positive. Okay. And so what is it that I want to do now? Well, I want to go back to this picture that I told you about in the first day of class, that you can really think of this Coxeter group as a system of mirrors where this is the only real room in the picture. So this is a physical room, and you have a mirror here, and you have a mirror here, and then these are just kind of reflections that you see, but really this is where you live. This is real life, and then these are just images. Okay. I want to make this precise in general. So to make this precise in general, I just defined for you what the real room is, D. Okay. And what I would like to claim next is that if I want to recover the whole picture, I basically just have to kind of move D around. Okay. So what does that mean exactly? What I want to say is that if I'm now anywhere in this real space, if I'm somewhere, then I can really think of this as the image of some point here under some mirrors. And that's my next proposition. So my next proposition is that every point in V is, now let me write it in an equation and in words. So a W conjugate and by W conjugate I just mean that you let W act on this guy mu. So I'm basically saying that my any point lambda is an image of a real point mu in the real what is called this is called the fundamental domain D. Okay, and actually this guy is unique. Okay, so again by W conjugate I just mean that it can be written as W times mu for some W, some group element. Now, So for example, what is it for some group element over here? And what is it that I want to do? Well, we kind of did this already. If I take some element here in this vector space, I want to say that this guy is the image of a unique guy in this chamber. Okay. Now, how do I figure out which chamber it is? Or which point it is, rather? Well, basically, what I'm going to do is just kind of use these mirrors to get back to the main domain, right? So this is the image of, I guess, something over here. And then this is the image of something over here. Okay? And so I'm thinking that if this is the lambda, then so this right here is lambda, then it's going to be an image of this mu. By which group element? Well, I have to first send mu over here, and S2 does that. And then I have to go over here, and what does that? What is this mirror? Well, remember that this mirror is the one that corresponds to this root, which the reflections are of S3 are S1, S2, and S1, S2, S1. And that's what this reflection does, is it multiplies by S1, S2, S1, or equivalently by S2, S1, S2. Okay? So I multiply on the left by S2, S1, S2, and what I get is that this is S2, S1. Okay. So this looks very reasonable in this picture, but we want to make sure that this really works everywhere, not just by looking at this picture. So that's what I'm going to prove now. Now, there's one thing that you might worry about. I mean, I think it's clear that basically, if you take one of these guys in the inside of one of these cones, then I think maybe it looks reasonable to you that you kind of land in a unique spot here. But for example, I don't know. Could it be that by reflecting in a different place, in a different way, you could get to this kind of the mirror image over here? Well, the theorem says that you can't. The theorem says that you kind of write to a unique mu. What that says, for example, is that you cannot take a point on this ray and reflect it around to land on this ray. Because these rays are both in D, and there has to be a unique representative in D. So let's prove this. First, let's prove existence. Okay. And what I want to do is the following. Let me define a poset on the positive roots. In this case, my positive roots are alpha 1, alpha 2, and alpha. Okay? And the way I'm going to define this is I'm going to say that lambda, or let me say beta is less than or equal to gamma. So these are positive roots, right? If they're positive roots, that means that each one of them is a positive combination of alpha 1 up to alpha n. Okay? And I'm just going to say that this one is bigger than this one if every coefficient of this one is bigger than the corresponding coefficient of this one. So when I write beta as, I don't know, b1 alpha 1 up to b k alpha k, and if I write gamma as c1 alpha 1 up to ck alpha k, and by definition, because beta and gamma are positive, the b's and the c's are non-negative. So I call this root smaller than or equal to this one if each coefficient here is less than the corresponding one here. Okay. So for example, what does this poset look like for this case? Well, what you have to do is take each positive root and write it as a combination of alpha 1 and alpha 2. Right? This is alpha 1 plus 0 alpha 2. This is 0 alpha 1 plus alpha 2. And this one right here, do you remember what it is? You can look at the picture. And this is a parallelogram. And so that means that alpha 1 plus alpha 2 is alpha. Actually, that's not something to remember. I don't think we had talked about that. But that makes sense, right? This is the diagonal of the parallelogram. So alpha is alpha 1 plus alpha 2. And so the way this poset looks in this case basically is that the top element is alpha, which is alpha 1 plus alpha 2, right? And then this is bigger than alpha 1 and bigger than alpha 2, because the coefficients of this one are bigger than the coefficients of these, and these two are in common. So this is how I define my poset. Okay. Now the intuition behind this is basically that alpha 1 and alpha 2 look like they're kind of the lowest roots, and I want to just say that as I move up over here, I'm getting higher into my poset of roots. That's more or less the idea. The point is that also I think it'll look plausible to you that this fundamental domain seems to be the part that is kind of farthest up. And so what I want to do now is take lambda, and to find mu, I'm just going to start reflecting and getting as high as I can in this poset. And I think when I get as high as I can in this poset, that'll do the job. Okay. So consider now I'm just realizing that I want to do this a little bit more generally, because I don't want to just define this for pi plus, but for arbitrary vectors here. And so what I'm going to want to do is define just an inequality of any two vectors in this space by saying that, I mean, remember that alpha 1 up to alpha k is a basis, right? And so that means that any vector in this space can be written uniquely as a combination of the bases. Okay? And so I can extend the same definition not just for the roots, but for any two vectors in my vector space. Okay? And so I started with lambda. I'm trying to find mu. And so what I'm going to do is basically just reflect lambda and send it up by using group elements and considering all the things w lambda such that they're bigger than or equal to lambda. Okay. Now, is there such a w, or could this set be empty? Well, the answer is that this is not empty. And there's a kind of a silly reason, which is that W is allowed to be anything. And so in particular, W could be the identity. Okay. And if W is the identity, then the identity times lambda is just lambda, and so this is trivially true. Now, let mu be the maximal, be a maximal element of this set. Okay. So let's think about it in this case. What am I doing? I started with lambda here. And I'm saying let's just allow my group W to move this lambda around. Okay? And we know what the images are. Well, we know that the images look like this, right? So basically, these are the things W times lambda. Now, out of those, I'm going to look at only the ones that are bigger than lambda in this poset. And what that means is that I only look at those where, to go from lambda to that one, I move positively in the alpha 1 and alpha 2 direction. So for example, to go from here to here, you see that I'm actually going in the correct direction. And so lambda is less than this guy in the poset, etc. Yeah? And so, I mean, one way to see it is just that it's just the things that are up here. Okay, these are the W lambdas that are greater than lambda in the poset. And now, out of all of these guys, I'm going to take a maximal one. And which one looks maximal to you here? Well, this one, right? Because you see this is less than this, and this is less than this. And so my claim is that when I do this, this is exactly the mu that I'm looking for. Okay. So my claim is that this mu that I chose is really in this fundamental domain D. Okay. How do I prove something like that? Well, basically, what is the fundamental domain D? It's the set of lambdas that has positive non-negative dot product with all the alphas. So let's suppose not. That means that I can find one of the alphas such that the inequality is violated. Right? Yeah. Meaning that you're on the wrong side of one of the hyperplanes. Okay. But then what I'm going to do is consider SI times mu. So what does SI do when I operate mu to it? Well, this is mu minus 2 inner product of mu alpha I times alpha I. Okay. If you look at this, you see that we know that this number is negative. Okay. And so this thing is mu plus a multiple of alpha I. And that means that it's in this situation. This is bigger than mu in the poset. It's mu plus positive things. Okay. And so what I have found is something that is bigger than mu, but also, I mean, mu was supposed to be of the form W lambda, right? And so this is SI W lambda. And so what I found is a group element that I can put to act on lambda and obtain a bigger root than mu. And that contradicts that mu was maximal. Okay. So this contradicting maximality. then that does it. That shows that mu really is in D, and that I can get from lambda to here by applying double. Okay. Any questions about this argument? Now, I said this was unique, okay? But so far I've only proved existence. And so I'm out of time to actually prove uniqueness to you. So what I want to ask you guys to do is to really look at this proof carefully, make sure you understand it, and try to see why this mu that I constructed here is unique, and then I'll prove that for you next time. Okay. But you should think about why, for example, you cannot take a guy here, a point here, and apply the group to it, and then land on this ray, for example.
In that picture, did the seal have one of the rays and not the other in it? Or did it have neither one?
It had neither one.
Neither one. Usually in arguments like this, you end up spending a lot of time figuring out a domain in which you have one but not the other.
Yeah, it was actually kind of surprised because what I remembered of this theorem, it kind of seems like you would want this to be closed and this open, maybe. But the key thing is this: that somehow the thing is that there are group elements that leave this guy's six.
Yeah.
And so the thing is that the mu that I'm talking about is unique, but the W is not. And that allows you to kind of. So there is no overlap between this guy and this guy, but there is kind of an overcounting here. There are elements of the group that.
Yeah. And you need to put both rays in there because maybe sometime later on you'll do
and also because if you open this, then you wouldn't have fundamental. If you want to make a statement that every element in the vector space is unique here, then you need this and you need.
Yeah, there are always two things that are perpendicular.
But like S1, S2 is not, so it's not one of these.
Yeah, but still, in analyzing Escher diagrams and stuff like that,
There's two things that are perpendicular.
when you're, it's not this, but the two-dimensional thing, you find a fundamental domain and you might be able to move it.
So there are six.
And you spend a lot of time on those, figuring out what's on the border, which ones, so that your arguments
We have
are
a
right.
Q really here. This thing in
Yeah, I think the
S4,
thing is, for example, if you looked at rotations,
12
then
vectors from a root.
if you wanted a fundamental domain for
Again, that's
the action of rotations, then I guess we would have to do
because
something
S4
like
has
this.
24.
Yeah, that's what I'm getting at, yeah.
But somehow because you don't really, in this picture you don't really allow yourself to rotate by this angle.
But see, he's saying you have 6 positive roots and 6 negative. You have 6 positive roots.
Where's that I want to say?
So he's saying that they're less now. So,
Well, we'll see what comes out of it.
Yeah.
It's what you're going to use this for to make that. Yeah.
You're gonna be in your office at 1:30 then?
Yeah.
Yeah.
Thanks for reminding that.
Okay.